All right, so the bright line spectrum and the Bohr model. So what evidence does bright line spectrum contribute to the model of the atom? First of all, bright line spectrums occur when you add energy to a source of atoms of a particular element. Turns out that when you excite those atoms by adding energy to them, they will then release very specific characteristic wavelengths of light. So here you see the spectrums for sodium and hydrogen. And I think it's probably a little hard to see, but sodium has a very intense line here in the yellow region. Hydrogen has a couple of faint lines down here in the purple or violet, and there's a blue line here and a red line here. And so what Bohr said was that these spectral lines represented energy transitions within the atom. And because of the structure of the atom at the time and the model of the atom at the time, they knew that those energy levels had to correspond to how the electrons were arranged around the nucleus. Remember with Rutherford's model, the nuclear model, we had the electrons moving in orbits around the nucleus. Well, what Bohr did was he said, all right, well, these electrons, orbiting around is okay, although he actually knew that was wrong because they would eventually cascade in on the nucleus. But the idea that the orbits had a certain radius that corresponded to a particular energy, and that only certain radii were permitted. Second, he said that the electrons in allowed states will not radiate energy and spiral into the nucleus. Now, I couldn't explain exactly why this happened, because moving charged particles should degenerate, should lose energy and come crashing in the nucleus, but this is one of his postulates. And three, that the energy is only emitted or absorbed by an electron when it changes from one state to another. And so this is again when we come back to that energy and how it's associated to waves and E equals h nu, the frequency. All right, so here are Bohr's energy levels. So if we have an electron at the lowest energy level, n equals 1, so if an electron all the way down here, if we add energy to that, we can cause that electron to jump up to a higher level. If it jumps up to a higher level, it then has a potential to fall back down again, releasing the energy. And it's the falling down that we observe, that release of a photon of energy when the electron goes from a higher state back down to a lower state. When the electrons are in the lowest possible state, that's called the ground state. When the electrons have been elevated up, they're in what's called an excited state. Bohr was able to come up with an equation that described the energy of these. And so you had basically Planck's constant, speed of light, and the Rydberg constant, R, gets factored into this number here. And then the 1 over n squared, the n represents the principal energy level. Now, unfortunately, Bohr's model couldn't explain or couldn't describe atoms with more than one electron. So his model kind of fell short there. But it did introduce the idea of quantized energy levels, and that in order to go from one energy state to another, you had to add energy to the electron, or energy is released when it falls back down again. The one thing we can do, however, is if we use, say, a helium atom, if we take an electron away from helium, so the helium would have 2 protons, 1 electron, that would be a hydrogen-like species, because it would only have 1 electron. The only thing that would change in this equation is that we would add a factor for the atomic number. So in this case, the atomic number for helium would be 2, right? 2 protons. And so we would plug that in there, and you would square that. So the energy associated with the helium would be increased by a factor of 4 for each principal energy level. Now, the other thing to notice here is that the Rydberg's constant, in front of it, there's a negative value there. What this means is that as you look at the energy levels, as you get closer to infinity, energy gets closer and closer to 0. So closer to the nucleus, you get to larger and larger or more positive values, whereas up at infinity, you get to a very, 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 very large negative number. Sorry about that. As you get closer to infinity, you get closer to a smaller and smaller negative value as you go up. So we'll do some calculations with this in class, so you get a chance to use this equation and calculate energy differences from one level to another.